Welcome to everybody. I said it already, and also those who listen to us via streaming it on Zoom and in the NITheCS community. And of course, a very welcome to our speaker, Professor Bucher from the University Cité, CNRS. And I'll now leave it to Francesco Petruccioni to introduce the speaker.
Thank you very much. So good afternoon, everyone, and thank you for your patience in this room and in Zoom. It's the first time that we try to do it live from here, so next time we will probably know exactly what can go wrong and fix it in advance. Yeah. Let me quickly introduce Martin. Martin studied did his PhD at Caltech with John Preskill, but only after having studied law, if I remember.
No, I did law after.
Okay,
yes.
okay. So anyway, there was a law connection somewhere. Yeah? And after that, he had some very nice postdoc position in Princeton, in Stony Brook, in Cambridge. And I think then he joined the Planck collaboration. And in 2004, he was one of the first persons that I met at UKZN. Because he was visiting there when I joined UKZN. And a few months later, he joined the University of Paris, University Paris Cité, number 6, 7.
Right, was it 11 first?
11.
I was at Orsay.
Okay. Anyway, somewhere in Paris. Yeah. And the last 10 days or so, he was visiting UKZN. And since yesterday, he came to Stellenbosch to visit us, and he kindly agreed to give us the talk today. Yeah. So, Martin, please.
Well, thank you.
Welcome to start.
Yeah, thank you for having me here. So I want to tell you a little about the microwave background, and some of this is going to sort of back up a little, because I think, and start with a little theory, because I think, one of the exciting things about the microwave background is that, when I started doing cosmology, people would say, well, this is philosophy. It's not a real science. There are no observations. And, in the last 20 plus years, this has really changed, and it's very hard to come up with new theories of the early universe that fit observation. That's not to say that the story is over. There's some sort of unsettling questions. There's this dark matter that no one has seen, so it seems. There's this dark energy that's sort of put in by hand to make the universe expand. So the story is by no means over. Let's see, is this? This is not. Oh, okay. Yeah, so I'll tell you a little about theory, and then talk about the Planck mission, which I worked on for 50 years. So this was a European Space Agency satellite to map the microwave sky in several frequencies. And I'll tell you a little at the end about the things that remain to be done, which are somewhat difficult. Let's see. Okay, so first, this is theory that goes back to Gamoff's papers in the late 1940s, which were very speculative, explaining, or trying to explain the various nuclear abundances, and also earlier in general relativity, there are these solutions where it seemed that the universe has to be expanding. But if you have a universe that's expanding, then from essentially zero size. Then as you go back in time, the universe becomes, very hot, just like in a diesel engine, you squeeze stuff and the temperature goes up due to adiabatic expansion. And you can see, this is the temperature of the microwave background today, around 3 Kelvin. And then, it basically goes back to infinity. And there's this postulated Planck effect. So, we don't know what the correct physics is. And then with particle accelerators, we can sort of explore some of this physics. This is atomic physics. And this temperatures where the universe became transparent. So the universe becomes electrically neutral, and there's no longer a lot of Thomson scattering. And the photons, the sort of glow of the Big Bang, comes to us today. So that's sort of the picture. And you shouldn't really believe this early part, but I think one of the points is that with cosmology, you can explore energy scales that are, many orders beyond accelerator experiments. So this is sort of what makes, one of the things that makes cosmology exciting. And this is a, diagram where we show one of the spatial dimensions. I put some general relativity, but you don't really need to know this. So the idea is, well, in this diagram, time is in the forward direction and photons travel at 45 degrees. And then, at this temperature of about 3,000 degrees, the universe becomes transparent. So basically, you look at the microwave background today and you see a picture of the initial conditions of the universe at this very early time. So, you basically see back to the putative Big Bang, that you see this huge sphere, because it's expanding. It's about 45 billion light years in diameter. And this is what we'll see. So we'll see some pictures of this. And the sort of history of this microwave background. Oh, this also shows up for everybody. Let's see, I can move this. Yeah, sorry about that. So this is slightly older than I am. There was this experiment at Bell Labs where, they were also studying communication noise at very high frequencies and doing radio astronomy. And they discovered thermal spectrum, basically with characterized by this temperature, and it was coming from all directions equally and obeyed approximately a black body spectrum. So this was consistent with the expanded universe theories, but these were observations that were, very crude. And then over the next 30 years, people tried to measure the spectrum more accurately and tried to find some non-uniformities in the spectrum, in the temperature. in the sky. And the problem was mainly the question of technology. You know, everyone knew that this was important. So with the anisotropies, the picture of the universe is that, you know, the galaxies that we have today and the structures, they arose from very small inhomogeneities, and gravity is unstable. So if there's a slight non-uniformity, things collapse. And you should be able to see these non-uniformities when they were small in the microwave background. And in that way, you can sort of test theories. Let's see. Okay, so this is really annoying. I haven't had this. Yeah. Okay. Let's see. This is energy in electron volts, and this is you know, various diffuse backgrounds. So here you have radio waves, microwaves, infrared, optical, X-rays, and gamma rays. And in astronomy, depending where you look, you see different things. So this is electrons zooming around in magnetic fields, and this is a cosmic radio background. This is the microwave background that comes from the Big Bang. The infrared is from dust that's heated by stars. Here are the stars, here active galactic nuclei, and you know, the more violent events at high frequencies. But we're just going to look at this frequency, which is, you know, centimeter and millimeter wavelength. So you see different processes at different wavelengths. Okay, so we go nearly 30 years later, and this is the COBE satellite from NASA, and in 1992, they announced the first detection of anisotropy in the microwave background. So that means that the temperature is not the same in different directions of the sky. And this, there are these radiometers. They're basically like radio receivers, and there's very fast switching between different pairs, and from these differences, you make a map of the sky. So this is what they did. This is the microwave horns, and then there's electronics, which switches back and forth, and these differences get recorded over several years, and the satellite spins and has a complicated scanning pattern over the sky. And here are the maps from COBE. So this is 53 gigahertz, so just an example. So if you just look at the sky, you see the same temperature everywhere, you know, with this color scale. But if we subtract away the constant part, then we see this dipole, which means that if we're moving relative to the microwave background, it looks, you know, blue in the direction that we're moving in red or in lower frequency in the opposite direction. So you see this pattern, and then you see these are galactic coordinates, and you can see, that there's some noise there. So this isn't really cosmology, it's our local motion. So you want to subtract away the dipole, and then this is what you get. So the galaxy is obviously very noisy, but then the question is what about what you see away from the galactic plane, and by analyzing at different frequencies and subtracting the galactic emission away, they made a first detection. So at that time, there were lots of papers, the COBE normalization of this or that model, and these could be compared to, the level of the non-uniformities required to, make galaxies and structure. So some models were ruled out at this stage. So this is a sort of simplified formula of when you look at the, non-monopole, non-dipole part, what do you see? So this is the relative temperature perturbation. And, there are various contributions. There's this intrinsic contribution. So, or the, photon, is a photon density higher there. So from the T to the fourth, you get this fourth factor. There's the Doppler factor, and there's the gravitational redshift term, not factor. And these get compared, at the now and then. And then there's also, if the gravitational potential is changing, you have photons that sort of speed up if they go into a gravitational well. So they would be blue shifted, but then if the well is shallower, the redshift from climbing out is not the same. So that's why you get this time derivative. So this is sort of what you see. We're here today, time goes up, and this is the surface of less scattering, which has some width. And, this would really be a huge sphere, and we can basically map some combination of these potentials out by looking at the microwave sky. Okay, let's go to theory. So how to interpret what you see. And this is from Martin Kuntz, a simulation or this visualization of cosmic strings. So this was a very popular theory at one point. So the idea was that things were completely uniform, but you had the symmetry breaking phase transition, and these very thin, heavy strings whiz around, and they gravitate, and they sort of stir things up, and they also go away in a self-similar way. So you have structure being formed continuously by these strings. So that was something that was very popular in the 1980s. And then the competing theory was cosmic inflation. So this was proposed by a number of people. So Alan Guth, I think, wrote the most clear paper of how this would solve a lot of paradoxes in cosmology. But his theory didn't quite work, and other people came up with a model that actually completely worked. And the motivation was a sort of classical theory that would make the universe very smooth and solve these paradoxes. But then later it was realized that there would be quantum fluctuations in this field, and the quantum fluctuations would become frozen in. And this could serve as the, seeds for the non-uniformities that later become galaxies. And this is a nice theory because, we would like to have a predictive theory. We wouldn't like if the non-uniformities were just initial conditions, then, it's just the way it is. Some supreme being would just put in things the way they were. But here you have a theory where things get completely smoothed out. So if there were something non-smooth before, you just stretch and stretch or inflate. So the non-uniformities go away, and then they get replaced with these quantum fluctuations. So a lot of astronomers at this time, now they all say, oh, well, we believe in inflation, but this was seen as, highly theoretical speculation, unlikely to be true. And the idea is, so this would be very simple. We just have there's also a gradient term, but this is a scalar field that is like a harmonic oscillator. So you could put an m squared phi squared. And here I draw a potential. And this is from the expansion of the universe. So this sort of looks like a friction term. And basically the field is kind of frozen, and you change the equation of state. So you get this exponential expansion, and that smooths things out. And then the scalar field sloshes back and forth and converts the energy into sort of ordinary matter and radiation. So this comes to an end. And we can make some sort of simple estimates. So this was a hard calculation. So this is sort of after the fact explaining it, that you get these fluctuations. The expansion rate or Hubble constant is 1/time. So it has the same units as a scalar field, which has units of energy. And then we can sort of, this gives you sort of extra expansion or a deficit of expansion because it retards a surface of constant density. So you convert this into a density fluctuation, and then you do the calculations, and you get some formula. And this calculation doesn't get the order of one factor, but it's basically right. And the same with the gravity wave. So you might say, well, we don't understand quantum gravity today, but we can linearize the, gravity wave modes, and just with a little courage, assume they're like harmonic oscillators, and you get something that is proportional to the height of the potential. So what you see here is the shape, the connection between the shape of the potential and the perturbations that you see. And this is the wavelength at which the modes freeze out, when the wavelength is equivalent to the expansion rate. So you get the large scales become frozen in first, and then the smaller scales later on. So you have a predictive theory. So let's go back to the observations. So if we have this temperature map and we start out with an isotropic state with these quantum fluctuations, it makes sense to expand in spherical harmonics and then take these expectation values, so that basically the only thing that matters is the angular frequency, or this would be like multipoles, in your mathematical physics book. And then we can average these. So this is a Gaussian process, and measure this power spectrum on the sky. And then you have codes that make the predictions for certain models, and then you compare them to the observation. So going back to the maps I showed you, so this is the data from 92, well, analyzed in a slightly different way. You see that it's basically flat, the power spectrum, and then what happens on smaller scales is not really, you can't see it. So one of the things at this point that people wanted to see, as I sort of explained, there were two vying camps: inflation and cosmic defects. And in inflation, the perturbations are primordial. So these harmonic oscillators are sort of set off with a very definite phase at early time, and then they begin to oscillate at later times. So you see these so-called acoustic oscillations. So these are like plasma oscillations in the photon baryon plasma. And so that's one prediction. And then with if the structure is being produced continuously, or things are being stirred up by these cosmic strings, then there's sort of no special phase. So you get a very rounded peak with, out this small scale structure. So one of the questions was, as you go to smaller scales, what are you going to see? And let's see, now this. And yeah, another question is non-Gaussianity. So in the inflationary theories, or the simplest theories, you basically have very small perturbations, and they're Gaussian, where the multipoles are very different, whereas in other theories you don't have that. So that's one thing you can test. Another thing, at that time, people didn't believe in an accelerating universe, or the astronomers just would see about 30% of the matter that is, implied by the expansion rate. So you could either put, say, oh, well, there's more dark matter and it's somehow very hidden, or you could say, well, the universe is just what you see, and it would have a hyperbolic geometry. And this can be done in inflation, where you have a single bubble and you put in the negative curvature in a very precise way. And this bubble expands, and then the field rolls down the potential inside the bubble. And this made a rather easy to see prediction that these acoustic peaks have a certain physical size that you can calculate. And if you have a hyperbolic universe, then the size of the spheres, rather than growing as the radius, it's a cinch of the radius. And so you see this sort of standard ruler from the acoustic peaks is that they should be at a much smaller length scale. So you can falsify this theory. If you see the oscillations, you can sort of read off the geometry of the universe. And it turned out to be, right on, where there's no negative curvature and a cosmological constant. So this is later data, and you can see these peaks being mapped out, and then these are experiments at smaller scales. So this really confirms inflation and or is consistent with inflation and consistent with a flat universe. So you saw these theories die. Okay, this is, I should have put this earlier. This was the first observation from Boomerang of the position of the first acoustic oscillation. So the multipole number is at about 220. Wait, this is not. Let me just go to, how am I doing with time? Okay, so this is the Planck mission. So this, the purpose of Planck was to map the microwave sky at higher resolution and greater sensitivity. And here you have basically a telescope, and then there's a focal plane that I'll show you. And this is electronics to send the data back to Earth. And you can see that this is sort of about the size of a car. And this was sent to the second Lagrange point. So it's very far from both the Earth and the Moon. And it scans the sky. And this is the focal plane. So you have these microwave feed horns, and the microwaves are collected, and then the outer detectors are basically radio receivers, and the inner ones are bolometers, which are basically elements that are absorb the microwaves at about 1/10 of a Kelvin, and their temperature is monitored. Okay, so you see, this is the frequency in gigahertz, and these maps are in galactic coordinates. In the low frequencies, you see the galactic synchrotron emission, and then it's lowest at about 70, and then dust takes over. So if you want to see the primordial emissions, you need to somehow subtract the dust and the synchrotron emission away. And you can take, roughly speaking, a linear combination. And here you can see that the galaxy has disappeared. So you could imagine just analyzing this map and taking the power spectrum. And this is the temperature power spectrum, and you can see the residuals. So the lack of fit here, except for this dip, which is a bit of a mystery, is due to, you're just observing a few realizations of the Gaussian random process, and then there are just 2l+1 moments, and then here the noise goes away, and you can see this tremendously good agreement with the best fit model, and these are the residuals. So you can ask, do you see any patterns there? Another thing that you can look at is the polarization, and so this is the polarized signal. And you see a very good agreement here. And this is the correlation with the temperature map. So this sort of provides an independent check of the quality of the fit. And one of the surprising things is that a very simple inflationary model where you just have a power law fits the data, and there are a number of undetermined parameters. You can measure the Hubble constant, you can measure the fraction of baryons, the fraction of cold dark matter, by implication, the cosmological constant, and these parameters are determined by at approximately the 1% level. Okay, so here in green you have the results from polarization and everything combined, and you can see that the polarization tells the same story. Okay, let me go a little faster because I want to talk a little about what is left to do. So this is inflationary models, and you can see this is the tilt of the spectrum, and then the amount of gravitational waves, and you can see that some models have been ruled out, and these are the observations that are going to get a lot better. So people are talking about measuring this ratio at about of the tensor contribution to about a part in 10 to the -3. So that would be at the bottom of this plot. Okay, this is gravitational lensing. Maybe how many minutes? Okay. non-Gaussianity. Let's see, there's a lot we could. Let me talk about the B modes, because I think this is the most interesting thing. So for the future, so we have these, I mean, polarization is sort of like a double-headed vector. So this is the, if you look at the sky, you know, what is the hottest direction if you turn your linear polarizer? And this E mode can be represented by a scalar potential, whereas this B mode, there's a 45-degree twist. So there's no way a scalar theory and, you know, the linear approximation can give you these B modes. And that's why if you want to measure the height of the inflationary potential, you know, the tensor or gravity wave oscillations only, they alone can excite the B mode. So you can look for these B modes, and they haven't been detected yet, although there has been one false detection. So that's sort of the future Planck has put limits on. And a lot of early theories sort of predicted a very large level, 10% or so, but they haven't been detected yet. This is sort of more the mathematical argument why, independent of models, if there's no nonlinearity and the perturbations are small, you will only get the B modes from gravitational waves or some other nonlinear theory. And here you see the various anisotropies with, so the green is the scalar contributions, and then the tensor gravity wave or in blue. And so, you know, these have a different shape. So if they were added to the temperature, if this were very large, here the tensor to scalar ratio is 10%. I mean, you would be able to detect it. But then if you go down to very low scales of energy scales of inflation, this curve gets moved down. And then this is the nonlinearity for gravitational lensing. So people want to look here at this bump in here and discover B modes. And that would be a very strong confirmation of inflation, because, you know, this is a new prediction. They wouldn't otherwise be there. So these are very long wavelength gravitational waves. They have a very red spectrum. It's not like the gravitational waves from LIGO. Okay, so there was a false detection at a very high level by BICEP. So this is this telescope at the South Pole that just measured in one frequency, and they thought, well, this couldn't be dust because no dust model would create a signal that large. So they, you know, made all these claims that made the New York Times and the Economist. And let's see. So this shows their two tenths tensor to scalar ratio and their best fit. And these are the previous measurements. So this was a you know, really remarkable claim you know, big surprise. Let's see these. Yeah, so what basically happened was they didn't have the parameters for the dust models, and then the Planck polarization maps were analyzed, and the signal was much larger. So this was sort of a false detection. So this is from a joint analysis with the Planck data. And this has been improved recently. So this is the same collaboration to 300s at 95% confidence. And then there are new telescopes underway. There's the Simons Observatory in Chile, and experiments at the South Pole. The US is planning this CMB stage 4 from the ground with hundreds of thousands of detectors. And there's also the Japanese have a space mission that is being organized called Lightbird that will be sensitive to about 30 times better than this, but it sort of remains to be seen whether the galaxy can be subtracted away. So what is the spectral index of the gravity wave mode? So this is, once there's a detection, you can ask you know, number of questions. So this should be 0, it should be scalar, scale invariant, or nearly so. Are the B modes Gaussian? Then there are also competing mechanisms possibly. Do they violate parity? So there are a lot of things questions that you could ask beyond just making a detection of the B modes. And you see sort of two strategies. One is from the ground, you can have many more detectors. You can access very small scales, because you can have you know, 10-meter telescopes. But then you have to look through the atmosphere, whereas from space, you can't have a huge mirror and only a few thousand detectors. So you get a lot of frequencies that you can't easily get from the ground. And it seems that both of these things are going to happen. So yeah, let's see. Yeah, so these are, so sort of the interesting thing about this is from Andrew Lang, who unfortunately is no longer with us, but he was sort of one of the leaders in CMB observation. And he said doing, you know, 90% of the effort comes from getting the last, you know, 10% of the results in this field is, you know, become really difficult, that you need, you know, in space, many thousands of detectors and hundreds of thousands on the ground. But the stakes are quite high because, you know, we would like to know whether inflation is really true, and we would like to also know the energy scale of inflation. So thank you for your attention.
very much, Mark.